Pi, the perfect constant, one whose real value eluded mathematicians from every era. Surely, everyone old enough has heard about pi before, but have you wondered why pi is what it is? Pi is commonly most associated with circles. It is present in a circle's area and circumference formula, showing that circumference over diameter equals pi. That is pi for you. Present in every angle too. 360 degrees equate to 2 pi radians. This is definitely not by chance. It makes trigonometry and calculus go hand in hand, makes the arc and sector formula much more elegant. Because of its importance in math, many minds sought the truth about it. Soon enough, pi was proven to be irrational and even transcendental, with each digit being as unpredictable as the last. Because of this property, the best we can achieve is an approximation, an estimation of pi close enough to its true value such that it can be used without much error. It seems so simple. Think about the common approximations of pi we use in math class or in application. 3.14. Maybe some use fractions like 22/7. But are these really the best estimations that we can get? Welcome to a video on estimating pi, where we will bring you on a journey throughout the mathematical world to search for the answers. This is our WOW project made by Elias, Wayan, and Ethan. We will first look at Archimedes' method for estimating pi, which used polygons to estimate a circle. It was first used in around 250 BC and was able to estimate pi accurate to 2 decimal places at the time. First, we will draw a circle of radius 1 and diameter 2. Now, we will inscribe a hexagon. It is easily proven that the side length of a hexagon is 1. We can see that the perimeter of the hexagon is smaller than that of the circle. By taking pi equals circumference over diameter, we can get that pi is greater than 6/2, which is 3. Similarly, we are able to inscribe a square outside the circle so that the side length of the square equals the diameter of the circle, which is 2. Now, the perimeter of the square is greater than the circumference of the circle. Since the diameter of the circle remains the same, we can get that pi is smaller than 8/2, which is 4. But why should we stop at a hexagon? Why can't we go further? The further we go, the more accurate it is, as the perimeter of the polygon will become closer to that of the circle. We can slowly change the inscribed hexagon into a septagon and eventually into a dodecagon. Here, each side is of length 0.5176. Since the diameter of the circle did not change, we can calculate pi to be greater than 6.2122 divided by 2, which is 3.1056. We can also gradually change the outside square into a pentagon and eventually into a decagon. The perimeter of the decagon is just very slightly bigger than that of the circumference of the circle, and each side length is of 0.6498. We can then evaluate pi to be smaller than 3.24914. Taking an average of these two values, we can get that pi is around 3.14734, which is accurate to 2 decimal places. In fact, you can do this for bigger and bigger polygons. Archimedes continued this process, doubling the number of sides of the polygons from 6 to 12 to 24 and finally 96 sides. He found that the lower bound of pi is 3.1408 and the upper bound is 3.1428.
Fast forward to the 17th century. we see a mathematician named Leibniz with a new way of estimating pi. This method is based on calculus, or not really, since calculus was not established in Leibniz's time. Instead, he used his own primitive method of calculus in his workings. For simplicity, I will show you the equivalent of his workings in modern-day calculus. Before we continue, let us talk about Maclaurin's series. Basically, it is the local representation of an analytical function as a convergent power series. It depends on calculus for the values of f'0, f''0, and so on. So feel free to learn calculus before this. We can also use summation notation to write this series. I will show you a simple proof for this series, assuming that the function can be represented as a convergent power series in the first place. We differentiate the function a few times in the hope of finding a pattern, and we shall see that we get one later. Now, what do we do if we want to extract information about the terms a1, a2, and so on from the equations? That's right, you substitute x equals 0 into each of the equations, achieving some really nice results. In fact, if you differentiate this function n times and substitute in x equals 0, we achieve the following, where n is a non-negative integer. From this, we can achieve the x to the power of n coefficient, an, by rearranging the equation. Finally, we achieve the formula for Maclaurin's series. We are now going to use our knowledge of this series to find an interesting estimation of pi. Here is the inspiration for our estimation of pi. In the introduction, we stated that pi is linked to radians, so how about some trigonometry? The arctangent of 1 is equal to pi over 4 radians. And now we link that to what we have learned about Maclaurin's series. Can we find a series for the arctangent of x? Although we can do it in other ways, let us convert arctangent of x into a function that is simpler to find a series of, specifically by differentiating arctangent of x to achieve the reciprocal of 1 plus x squared. The series for the reciprocal of 1 plus x squared can be easily derived, and thus is left as an exercise to the viewer. In fact, it can also be derived from the binomial series. Substituting this into our equation and rearranging, we eventually achieve the desired series for arctangent x. Do note that since indefinite integrals produce an arbitrary constant c, we need to find c in this case as it becomes non-arbitrary. After substituting the magical x equals 0, we see that c equals 0. And there we have it, the desired series for the arctangent of x. Let's put it to good use to find pi over 4. Behold the Leibniz formula for pi. It was published by mathematician Gottfried Wilhelm von Leibniz in the year 1676. Although it shows pi over 4 in most versions, very trivially, we can estimate pi from pi over 4. Adding a finite number of these terms from the infinite series will give an estimation of pi over 4. The more terms used, the higher the accuracy of the estimation of pi over 4. There is also another method of proving this which I would like to share with you. Follow me into the world of complex numbers for an elegant proof. Here is the inspiration for the new proof. Consider the Maclaurin series for ln x plus 1. It looks similar to the infinite series in the Leibniz formula. The real question is, how do we make it exactly like the series desired? Well, it's simple. Substitute x equals I, where I, which is an imaginary number, is the square root of -1. After substitution, we realize that the imaginary part, or the coefficient of I, is equal to what we desire. What is left to show is that the imaginary part of ln I plus 1 is indeed pi over 4. Now, how do we evaluate such a value? It seems impossible, but there is actually a way. To discover it, we have to go into the topic of complex numbers. Complex numbers are numbers that have a real part and a part with I, where I is the square root of -1. Therefore, we can represent any complex number in the form x plus yi. X is the real part, while y is the imaginary part here. Now, we have a sneaky method to convert this into something else. Why not plot this on a graph, where coordinates x, y correspond to the complex number x plus yi? Let's try that out. Such a plot is an Argon diagram. I even added a few more lines and angles. We call the complex number z, and that is equal to x plus iy. Using trigonometry, we can put x and y in terms of the new variables r and theta. R is usually called the magnitude of a complex number and can be found by Pythagoras' theorem, while theta is known as the argument of a complex number and can be found via trigonometry. There we are, but there is more. Yes, we are using Maclaurin series again. We assume it can be used for imaginary numbers as well. This time, we use the series for sine x, cosine x, and e to the power of x. You will see why soon. After some simplifications, we get to the conclusion that the series of our complex number z is equal to the series of re to the power of I theta. Take a look at the working on the screen and you will realize why. This is Euler's formula for complex numbers. Going back to our 1 plus I, which would be substituted in later, we realize that we can draw it on the Argon diagram as well. Now, we find the magnitude and the argument of this complex number. Then, we can put the complex number in the desired exponential form. This will be easy to substitute into the ln function as it would simplify nicely. Recall that we want to find the imaginary part of ln 1 plus I. After converting 1 plus I into its exponential form and simplifying, we see that we indeed achieve pi over 4. With this, we can get the Leibniz formula for pi again.
In 1706, a mathematician named William Jones published a piece of work titled Synopsis Palmemorium Mathiosos. In it contained a formula which looked like the following. This formula was used to calculate the first 100 decimal digits of pi, a record at the time. So, who made this formula? Well, it was a mathematician named John Machin. Here's a cleaner version of the formula shown on the screen. Now, this formula raises a few questions, like how did John Machin come up with this formula, and how was it so accurate for his time? To come up with this formula, we will invoke concepts expanded on in the previous part, in particular, complex numbers and Maclaurin series. Here's our three-step approach to the formula. Firstly, we will show that 5 plus I to the power of 4 is equal to 2 times 1 plus I times 239 plus I. Next, we will use the arguments of complex numbers to prove this formula for pi shown on the screen. And finally, we use Maclaurin series to expand our arctangent formula into the one John Machin contributed. Firstly, by the binomial theorem, we can expand 5 plus I to the power of 4. Next, we'll simplify I squared, I cubed, and I to the 4th into -1, -I, and 1 respectively. Now, we collect real and imaginary terms together. Evaluating each of these gives us 476 plus 480 times I. Now, we will perform a series of manipulations to factorize this expression. Finally, we obtain the desired expression, completing step 1. For step 2, we will use the well-known fact on arguments of complex numbers to convert the product into a sum of arguments on the right-hand side. Then, we convert arguments into angles as arctangents using the definition of the argument as an angle. Note that the arctangent of 0 is 0 and the arctangent of 1 is pi over 4. Now, we make pi the subject of the equation, and this completes step 2. Now, armed with our formula for pi, step 3 is easy. We simply make use of the Maclaurin series of arctangent covered in the previous part and apply it to our formula. Next, combine the two sums into one. Finally, expand out the terms of the sum and see that it's the exact same as Machin's formula. This concludes step 3, but the question remains, how was this formula so accurate? First, some terminology. We define Sk as the sum of the first k plus 1 terms of the infinite sum. We'll visualize the sum converging to pi using a graph. For terms greater than pi, Sk is blue, and for terms smaller than pi, Sk is yellow. As you can see from the graph, the sum alternates from being blue then being yellow, thus from being greater than pi to being smaller than pi. This means that the distance from one point to the line, or the distance from Sk to pi, is less than the vertical distance between adjacent points Sk and Sk minus 1. In other words, the absolute value of Sk minus pi is less than the absolute value of Sk minus 1. The right hand side is the k plus first term of our sum, while the left hand side is simply the error between our truncated sum Sk and pi, so this allows us to estimate how fast the error decreases, and thus how fast the accuracy increases. We will ignore the 1 over 239 factor as it decreases much faster than the 1 over 5 factor. And after some algebra, we'll get this expression. Focusing on the 1 over 25 term, it tells us that each new term in the sum decreases the error by about 25 times. This explains how the formula is so fast. In fact, a naive estimate of how many terms needed for 100 decimals of pi can be done. The error has to be less than 10 to the minus 100, so using our error estimate and some algebra, we get that k is about 71, so we only need to sum 72 terms. In reality though, this number is even lower as our bound is still quite rough. This method of using arctangents is fittingly known as Machin-like formulas, and they are still relevant today. In 2002, the record at the time for digits of pi was a massive 1.24 quadrillion, obtained by using the two monstrous equations shown on screen. And with that, we have come to the end of my part. Thank you for listening.